Today in physics, we're going to talk about angular momentum. We're going to talk about momentum of individual particles and momentum of solid objects. Angular momentum is similar to linear momentum. Remember, linear momentum is a product of an object's mass and its velocity, and it's a vector. Angular momentum is a quantity that tells us if you have something spinning, how hard is it to stop an object from spinning? Or how hard is it to turn an object that is rotating? And it talks about this quantity, angular momentum. If you have more of it, then you're very, very stable and it's more difficult to change the object. Objects that have a lot of momentum are in a very stable position. So we've kind of talked about the spinning wheel before and how if we take a spinning wheel and we rotate it about a certain axis, if I spun it about this axis, it's not very stable and it gets wobbly. But if instead I spun it about this vertical axis, it can become very, very stable. And if I spin it really fast and then set it down, of course, we know that it can stay spinning for a long time. When we talk about angular momentum of an object that's rotating, it doesn't have to be a small object like this wheel, but it could be something that's very, very large, like our solar system, which is rotating about sort of a fixed axis, or an axis that kind of changes as the planets get around. It would essentially be rotating about its center of mass system. So for an individual particle that has a momentum already, so we've got a particle and it's moving, the angular momentum can be found with this relationship. So angular momentum is the symbol L, and L is kind of like torque R cross force. L, momentum, is radius times linear momentum. So L is your angular momentum. R is the distance from that particle to the point of rotation. So think from the pivot point out to where that particle is. And then finally, P is your linear momentum, which is a product of your mass and your velocity. So let's take a look at an example problem here. So this says, determine the angular momentum for the revolution of the Earth around the sun and for the revolution of the moon around the Earth. So first, let's talk about the Earth going around the sun. To find angular momentum, L, we need radius and we need linear momentum. So that would be the radius from the Earth to the sun. Obviously, that's not a fixed distance, it does change, but we'll just take the average distance from the center of the sun to the center of the Earth. Then we would multiply that by the linear momentum. So that would be by the mass of the Earth and the velocity of the Earth. Now remember, we want R and velocity to be perpendicular to each other. So this will be radius times mass times velocity times the sine of 90 degrees. So how about the velocity of the Earth? When the Earth is going around the sun, how could we figure out how fast that's moving? Well, remember, velocity is just distance divided by time. And if we assume a circular orbit, which it's not, but if we did assume a circular orbit, that distance would be 2 pi r divided by the time to go around the sun. So that would be 2 pi times 149.6 times 10 to the 9th meters, average distance, divided by the time to go around once, which would be 1 year. So if we did that calculation, we could get a velocity of 29,786.5 meters per second. So we kind of worked out the radius and the distance and the time there for you. So now to get the momentum, we need the radius times the mass of the Earth times that velocity. So the radius of the Earth, we said about 149.6 times 10 to the 9th meters. The mass of the Earth, 5.97 times 10 to the 24th kilograms. And then times the velocity that we found of 29,786.5 meters per second. So you can see this is going to be a very, very large number. So we get 2.66 times 10 to the 40th. And then the units for this are kilogram meters squared per second. So that is a lot of momentum. That's a good thing. Our Earth going around the sun has a lot of momentum, and that would mean it would take a tremendous amount of energy to change the momentum of the Earth going around the sun. For us, that creates a lot of stability and a lot of security. Let's talk about the moon as it goes around the Earth. And I'll talk about the direction of that as well for you. So the moon going around the earth, that angular momentum still is going to be L is R cross P. So this is a right-hand rule product. R cross P means I want the radius to be represented by my index finger and the momentum to be represented by my second finger. The part of that would be the velocity, like which direction is the velocity object, and then my thumb would represent the momentum. So that's going to be the radius from the moon to the earth times the mass of the moon times the velocity of the moon. So first let's figure out the velocity of the moon. Remember, that's simply just distance divided by time. So 2 pi r divided by t. But the t for the moon to go around the earth is the period of the moon's rotation. That's 27.3 days. So it'd be 2 pi times 384 times 10 to the 6 meters divided by 27.3 days. If we convert that to meters per second, we get a velocity of the moon to be 1,022.9 meters per second. Now that we know the velocity of the moon, we can find the angular momentum of the moon by doing L is radius times mass times velocity. So once again, the radius from the earth to the moon, 384 times 10 to the 6 meters, times the mass of the moon, which is 7.36 times 10 to the 22 kilograms, and then times the velocity, 1,022.9 meters per second. So when we talk about what direction is this orbiting, then to right-hand rule this, we would need the radius and the velocity. And much like anything going around in any circle, in this example, if this was kind of representing the sun was at the center here and the earth or the moon was going around the sun, then we would have a radius, say that we're out over in this place, we would have a radius like this and a velocity coming forward to you, so the direction of the momentum would be up from the plane of rotation. The same thing is true about the moon going around the earth. We would, if this was the earth and the moon was out here, then the radius would be, from the earth out to the moon. The velocity of the moon, if it was coming toward you, so if our moon is rotating, if you're looking at it from above, if our moon was rotating counterclockwise, so the velocity coming toward you, and once again, the momentum would be up from a plane of the solar system. This momentum for the moon would be 2.89 times 10 to the 34th kilogram meters squared per second. Also in that same direction, up from the plane of rotation of the solar system. So what if you have a much smaller scale? Let's take a look at this example. Here we have a coordinate system, x and y axes. We have an origin. This has been marked off by every tick mark represents 1 meter. And this asks us to determine the angular momentum for the 2 kilogram particle shown if it's going around the origin. So here we have a 2 kilogram particle represented by this red dot. It has a velocity of 3 meters per second in a downward direction. So if we're looking at the origin and we want to know what this momentum is, we say L is R cross P. So that will be the radius times the mass times the velocity times the sine of 90 degrees, because once again, the velocity and the radius are perpendicular to each other. So we would take our radius, which is 2 meters, our mass is 2 kilograms, and our velocity is 3 meters per second. And so if you multiply 2 times 2 times 3, you get 12 kilogram meters squared per second. Notice that this says it's in a negative z direction. Let's see if we can right-hand rule this and figure that out. So our radius is from the origin out to the dot, so that would be r. The velocity would be represented by your second finger, so we're going to point down. And then our thumb would point into the screen to represent the direction of the momentum. So that's why this is a negative z direction, right? Remember, we have negative x and positive x, positive y and negative y, negative z into the board, positive z out of the board. So what about if we want to look at this position of x equals 2 and we want to find the angular momentum about that position? Well, we would still go about it the same way. We would say, okay, L is R cross P. So that's going to be radius times mass times velocity times the sine of the angle between R and V. And so if we look at the radius of our particle around that position of x equals 2, well, that's 0 meters. And then times 2 kilograms times 3 meters per second, which gives us an angular momentum of 0 kilogram meters squared per second. So the interesting thing to note about this is that this particle does have linear momentum at that point. It just doesn't have any angular momentum respective to that position, respective to the 2.0 position. Okay, and so sometimes you can have linear momentum and not have angular momentum, and that's fine. Okay, so there's a Minute Physics video I would encourage you to take a look about angular momentum. You can just click on that link. But let's talk a little bit about angular momentum of a solid object, because we've said if it's a point particle, it's radius times mass times velocity. But if you have a solid object like a ring or a solid sphere or a hollow hoop, like how do we deal with that if those things are rotating around a fixed point? So for a solid object, angular momentum is similar to linear momentum of a solid object. Remember, linear momentum, P, is mass times velocity. So we're going to replace momentum with angular momentum. We're going to replace mass with rotational inertia, mass distribution, and we'll replace velocity with angular velocity, or omega. And we get a new equation to find the angular momentum of a solid object, and that is L equals I times omega. So we said L is R cross P if I have that information available to me, or if I have a solid shaped object that I understand what the inertia is of that object, and it's rotating, then I can use L is I times omega. So let's take a look at this kind of an example. This is calculate the angular momentum for the rotation of the Earth around its own axis. And it says the I of the Earth, which would be a solid sphere, is 2/5 mr squared. So Earth is spinning around its own axis, and because it's rotating about a fixed point, it has angular momentum. We can't do radius times velocity because the Earth itself has different radii at different points, and each of those velocity have different values depending on how far away they are, linear values depending on how far away they are from the axis of rotation. So we want to handle this a different way. So we want to say the angular momentum of the Earth in this case would be I omega. So I times omega, and I was given to us 2/5 mr squared, and then omega. What is omega? Omega is angular velocity. How fast are you spinning? Well, that is how far do you go around divided by how much time it takes. Within one rotation, you travel 2 pi radians. And then to go around once, we call that your period of rotation. So omega is going to be 2 pi divided by t. Now we're talking about the Earth going around its own axis, so this will be 2 pi divided by 24 hours. So 2 pi divided by 24 hours converted to seconds gives us an omega of 7.27 times 10 to the negative 5th radians per second. This is a really small rotational velocity. That's good. You and I couldn't handle a really fast rotational velocity. That fluid on the inner side of our ears, it helps us with balance. And so if we were spinning that fast, we would be dizzy. So it's kind of nice to have a small angular velocity here for our perspective. All right, now it doesn't matter where we're at on the Earth, we would still have the same omega. So if we're trying to say angular momentum L is I times omega, then that would be 2/5 mr squared times omega. So it'd be 2/5 times the mass of the Earth times the radius of the Earth squared. This is the average radius of the Earth squared times omega. And so we would get the angular momentum of the Earth to be 7.07 times 10 to the 33rd kilogram meters squared per second. What direction is this momentum? Well, whatever direction the angular velocity is, that's the same as the angular momentum around that axis. The last thing we need to talk about with angular momentum is that momentum is one of the 2 big laws in physics about conservation. As long as you have a closed system, there are no outside torques or outside forces, then the total momentum of the system is always conserved. The same thing also holds true for angular momentum. So the law of conservation of momentum states that the momentum of a system will not change unless an external force is applied. How would you change this statement to create the law of conservation of angular momentum? We would say the angular momentum of a system will not change. Instead of saying an outside force, we would say there's an external torque on the system. So the momentum before any scenario will always be equal to the momentum after that same scenario if there are no outside torques. You see this very frequently with like figure skaters who are spinning and then they take their arms from an outside position and then bring them in close to their body and their velocity really increases. Or they take their arms out when they finish this performance, they go ta-da, and all of a sudden by increasing this rotational inertia, omega has to get smaller. So they don't go ta-da so that you'll know when to clap and be like, yay, good job. They go ta-da so that they can stop. So let's take a look. Here's a figure skating question. It says a figure skater is spinning with an angular velocity of omega naught. He brings his arms and legs closer to his body and reduces his rotational inertia to 1/2 the original value. What happens to his angular velocity? So remember, the momentum after and the momentum before have to be the same. And the momentum is I times omega. We can't radius times velocity for the figure skater. So we have to I omega for the figure skater. So I omega after equals I omega before. So if we assumed that his after is 1/2 the before, right? He says he reduces it to 1/2 the value. Then we would say that 1/2 I before, because that's I after, times omega after equals I before times omega before. And therefore, if you try to solve for the omega after, you get twice the omega before. So as he brings his arms in and reduces his inertia to 1/2, the angular velocity will double. It will increase his speed. And that's conservation of angular momentum.